So good evening everyone. Let us get started with our discussion. I'll briefly recapitulate the quantitative discussion that we had while comparing the inductance and resistance values of the two windings that we have in a DC machine called the field winding and the armature winding, and thereafter we'll go towards understanding induced EMF. uh, why does voltage get induced in what are the scenarios in which it gets induced, and why do we see that in the armature voltage, why not in the field? So all those things we'll discuss today. So to start with, uh, so maybe I will briefly discuss the quantitative things that I have discussed yesterday, last class. Then I'll stop for questions if you have any doubt on that. So we are going to start with, so MMF. The first condition that we discussed is the requirement. We have certain requirement for MMF, and MMF required is, say, F equal to Ni, and that is constant, that does not vary. So once it is clear how much MMF we require, that is known and that is constant. So that is the first case. Then next, because we have some winding, so winding will have some resistance, and we saw that resistance is nothing but rho L by A. L is the length of the coil is proportional to the number of turns that we are putting, and the A is nothing but current by current density. So if we put these two things, then what we find finally is R is proportional to Nj by I. That was our second equation that we got. Third equation is voltage constraint. So there is always, once decided, we want some voltage to be applied across the winding. So that is also a condition. And for DC machine, mostly the voltage, this is voltage that is getting dropped as resistive drop. That may not be the total voltage, because armature voltage, a part of voltage goes as the induced EMF. So we have to apply some higher voltage than the induced EMF. So here I can say voltage that is for resistive drop, IR drop. That is the voltage I am talking about. So voltage is equal to Ri. So if I put this R, what it is dependent on, then we will get voltage is proportional to number of turns into current density. That is the third equation that we had. Fourth equation, if I go, fourth equation I discussed about volume of copper. That is also another important criteria. Because copper has some value to it, so we cannot put more copper than necessary. So we want to get a quantitative idea about how much copper that we are using. So volume of copper is proportional to, is basically the volume of copper is nothing but the length of the copper wire and cross sectional area of the copper wire. So it is proportional to length multiplied by cross sectional area. So if the previously derived things are used, like L is proportional to N and A is basically I by J, if those are used, then finally we get Vc, the volume of copper that we require, that becomes proportional to F by J. Then another condition is efficiency. Our things should be efficient. So losses, the copper losses that is taking place, we have to have some quantitative understanding about that. So losses, P is equal to I square into R. If we similarly put the things, then we got that the power loss is proportional to MMF multiplied by current density. So numbering it as 4, numbering it as 5. So we got 5 constraints. So what can we see? What can we see uh, from say equation? Let us now focus on the fourth equation, equations 4 and equation 5. Equation 4, you can see that uh, the volume of copper is inversely proportional to J, because MMF is constant once we know our requirement. So if we go for higher J, then what will happen? Our copper requirement, so VC, volume of copper that is required, that will come down. But equation 5 tells you that for the same MMF requirement, if we use higher current density, that is higher J, then P will actually come up. So our volume, our copper cost, that will volume of copper, that will go down, but our losses, say electricity, for electricity whatever is the corresponding rupees to that, that will increase. So electricity bill will increase if we go for higher J. So there is a thing there. And on the other hand, if we go for lower J, lower current density, then equation 4 tells you that the volume of copper, that will go up, and on the other hand losses will go down. So clearly you can see that there is something to optimize. There is a optimal point where uh, where uh, at which current density the volume, you will not use more volume of copper than necessary, and you will also uh, 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 not lose much, so you will not end up having a lower efficiency. So if I try to plot the equation 4 and equation 5 in a graphical sense, then if I let me plot volume of copper versus J, and you can see it is inversely proportional, so it will be hyperbolic like this. So this is volume of copper versus current density. If you go to very high current densities, then the volume that you will require is very low, and if you go to very low current densities, then the volume of copper will actually go high. Now let me plot for the power loss versus current density. You can see that it is proportional to current density, so you get some line, you get some straight line. That is, if you have low current density, then no current, then zero power. If you increase the current density, then your copper loss gets on increasing. Now we have to form another parameter, another function that we need to reduce. So always we want to reduce cost. So everything, the volume of copper as well as the power loss, they can be expressed in terms of rupees. So some cost in terms of rupees. So say we require K1. K1 rupees is required per watt loss, right? And K2, let's say K2 is the rupees for 1 meter cube copper, right? So these are the rupees numbers corresponding to the power loss and the volume. So if I try to write the cost function C, so for say let us say P is the power loss that is happening, and we require VC, volume of copper, then the cost in rupees will be K1 into P plus K2 into VC. So this is the cost function, and if I try to now plot the third one, that is cost with current density, because both cases current density is the common optimization variable, which the variable that we are going to optimize for the optimization. So that is J. So what will that be? That will be the summation, point by point summation of these two earlier plots. So if I indicate the straight line as a dotted one, then you can see that when j goes to, let me use a different color, when j goes to a very high value, then the volume actually goes to almost zero. So at infinity of infinite j, you can, these two will, vc requirement will be zero. So at higher j, the cost curve will be closer to closer to whatever is the value corresponding to the power. So the actual, if you say this is the j value, if you sum this, uh, anyway both are getting multiplied by say k2 and k1, but the shapes remain the same. So whatever is the value of k1p at j, this one will be, so the cost value will be mostly very close to that. And as j value increases further, it will go and meet this dotted straight line corresponding to the second curve k1p versus j asymptotically. So this is the one. And on the other hand, when j is very low, say it is 0, then this curve actually goes to infinite asymptotically. But that does not make any physical sense, because j equal to 0 means we are not sending any current to the winding. So if we look at some very low j, then this is very high and this is actually 0. So whatever is the value k2vc here, that one will come here, and in between we will see some trend like this. So finally, if you plot c versus j, you will find some curve like this. And you can clearly see that this cost function, that has a minimum point. So there is some j value, let me say name it as j optimal, where the cost function, the c, actually comes down, or is at its minimum point. So that is the j optimal. So that is the optimal value of current density that we should use while designing this machine. So this is just a brief, giving you a brief understanding about design. Now, are there constraints? So these are the different conditions that I have discussed. Now we have to discuss about the constraints on j. Constraints on j. So obviously our current density should not be very high and current density should not be very low. They are decided by two factors. So one is, you can see that if you go to higher and higher j, then the losses become actually quite high. And if the losses become more than certain value, then it becomes difficult to dissipate that loss. So uh, there is always a thermal limit. So one constraint is thermal limit. That limits what is the J max that you can go to for your cooling system. Suppose you have a liquid cooled motor. Suppose you have a motor which gets cooled by a fan connected to it, or the motor just remains in the atmosphere, and the atmosphere alone cools the motor. So for the first case, if you have a liquid cooling, if you have some cold liquid circulating around the motor and that is taking away the heat, you can actually push this Jmax to very high numbers, compared to the case where the motor is kept in the environment and you have nothing to cool the motor. So there is always a Jmax that is decided on based on the thermal limit that you have, and that may be somewhere, say this is Jmax. That depends on some thermal uh, limits. So your thermal equivalent circuit, you have to look at that. You have to look at your cooling, so thermal heat flow. So basically heat flow, you can thermal equivalent circuit that will basically tell you what is the heat flow and temperature rise. So this is the thing, and also with that, so temperature heat flow is something, and temperature rise will be obviously decided by your cooling system. So the J max that you are up to which you can go to, that actually depends on these factors. So that puts a limit on J max, right? So you have a limit on J max. So this is the first constraint. You have a second constraint also. Second constraint is what is the area available area that you can, available area for copper, area or volume, whatever you call, volume for copper. So you can see if you go to the earlier slide, you have some, once the machine dimensions are fixed, you have some area or some volume that is available where you can put your copper. So your VC max, the maximum volume that you have at your disposal, that is already fixed one as soon as you decide on the other machine dimension. So VC max is already fixed, and this actual VC, that has to be always, actual VC has to be always lower than your VC max. And actual VC is, what is actual VC? That is some constant multiplied by F by J. So say some constant by J. So VC is basically some constant, say K by J, that has to be lower than VC max. So you have some VC J min, that so J min has to be, so J will have to be greater than some number. J has to be always greater than some number K by VC max. So K is the proportionality constant for this fourth equation that takes care of the MMF F also, and VC max is the maximum available volume for copper. So that decides on the J min. So J min actually can be it may be lower than J optimal, or it can so be that it can be higher than J optimal. Then we do not have any other option than uh, uh, than choosing that corresponding J value only. So it depends on our particular case. So we have, suppose we have our J minimum here, then actually we can actually choose the optimal point that we can find from the optimization, where the cost actually becomes quite low. Now this is the whole discussion. Now let us try to compare the field winding and armature winding. So we have these two windings. So which one? Let us first try to look at from the perspective of copper area or volume availability. So already we have seen that field winding, because that is put on stator and you have lot of area available. So whatever is the volume VC, say max, for field winding, that is quite high compared to VC max for armature winding, because for armature conductors are only put in so small slots. So obviously the J minimum for field, whatever you have, that will be quite low compared to the J minimum that you can have for armature. That is directly coming from this relation that we have derived, that J minimum is inversely proportional to the VC max. So J minimum of field winding is quite low compared to J minimum of armature winding. So this is one condition that comes. Then the second condition will is the voltage drop across the resistance. Let us say we have same voltage for the field winding as well as the armature winding, but as we will eventually see, the voltage on the voltage on applied across the field winding goes totally as the IR drop in steady state, because it's a DC current that flows and there is no induced EMF. But on the armature coil, we'll see that there is some significant back EMF, some induced EMF. So maximum major portion of the voltage actually goes uh, goes as or is equal to the back EMF that eventually comes up. So the voltage, effective voltage across the resistance of the winding for the field winding is very high compared to the voltage across the resistance of the armature winding. So you have these two conditions. So if you now look at the number of turns. So if I go back, so voltage, where is the voltage equation? So this third equation, this can be written voltage is equal to some constant k into nj. So the voltage is equal to some constant k into nj. So number of turns, that is equal to 1 by k into v by j. So number of turns is actually proportional to the ratio of voltage across the resistance divided by j. Now you can see that Vf, this is the equation, your equation 1 or equation A, and this is your equation B. So your Vf is greater than Va and J min F is greater than or is less than J min A. So if J min F is proposed, then 1 by J min F is actually greater than 1 by J min armature. So this is the modified equation B, and if now equation A and B are multiplied, then you will find that Vf divided by J min F, that is high compared to V armature divided by J min armature. So this is nothing but this ratio depends or is proportional to the number of turns that you have. So this clearly tells us that the field winding that is generally used or employed or to be employed, that is quite high than the number of turns in the armature winding. So this is the first thing that comes out when we try to compare the two windings. Now the self-inductances. The self-inductances, they are basically number of turns divided by reluctance. We have already seen the reluctance of the armature. Let me write field first. So reluctance of the field winding is very low compared to the reluctance of the armature winding. So 1 by Rf is very high compared to 1 by Ra. This becomes our equation C. And again, Nf square is very high compared to Ns square. So if you multiply equation C and D, then we get Nf square by Rf is very high compared to Ns square divided by Ra. So that tells us that the inductance, the self-inductance of field winding is actually very high compared to the self-inductance of the armature winding. Now similarly, if we go to the resistance, now resistance is again dependent on, we'll remove part of that. So this concludes the discussion on inductance. Now if I try to look at the resistance is So because NF is very high compared to NA, that means the length for the field winding is very high compared to the length of the armature winding. Now if we for now if we assume that the whatever is the mmf required for the field winding, that is approximately equal to the field or mmf in the armature winding, then because we have nf, the number of turns of our field winding, very high compared to na, and f is nothing but ia, then this clearly tells us that if has to be quite high, quite low compared to ia, because nf into if is equal to a into ia. So this is coming from the assumption that both these armature and field are require almost the same mmf, even if not exactly same, but there will not be orders of difference. So if it one may be 90% or 95%, 85% for of the others, but they are not half of one another. One is not half of another. So clearly the field were, if because they are approximately of the same order, then number of turns, very high change or difference in the number of turns comes as very major change in the current that it has to flow. So if we require a very low current flow to the field winding, then why to use a higher cross sectional area? Why to use a higher cross sectional area? Where for that? We can simply use a lower cross sectional area where for the field winding. That means the cross sectional area is low compared to the armature winding. Now resistance is proportional to L by A. Now so LF is greater than LA and AF is lower than AA. So 1 by AF is greater than 1 by AA. Again, let us say this becomes our equation E, this becomes our equation F. Multiply equation E and F, we can clearly see that the field winding resistance is very high compared to the armature winding resistance. So this concludes our discussion on the relative values of inductance and resistance of the two windings. So is there any question? I have clarified this once more, the whole process for so that there is no doubt in that. So is there any question or it is clear now?
Yes, I clear.
Okay. So now let us try understanding what do we mean by induced EMF. So Faraday tells that there is, if we have any coil, Faraday's law of electromagnetic induction, and if this coil is in some magnetic field, so magnetic field, the flux lines link the coils of the field of this coil, of this winding basically. So there is some flux linkage. We understood what we mean by flux linkage. And if the field which is there in the environment of this winding, that keeps on getting changed due to some reason, then the flux linkage of this winding will also change. So there is some change of the flux linkage with time. So there is some non-zero d psi dt. So as soon as there is some non-zero d psi dt, Faraday's law of electromagnetic induction tells us that then there will be some voltage induced across the winding. So that is Faraday's law of electromagnetic induction. We will not go into the science like the Lenge's law. It will try to oppose. We will not go into that. But if we focus on the magnitude only, if we have some winding which sees some rate of change of flux linkage, then there will be some induced EMF. That is what Faraday tells us. Now we have already discussed about self-flux linkage and mutual flux linkage. So what do we mean by self-flux linkage? If the coil in question that is carrying some current and the flux lines are due to
So
that.
your voice
Is my voice clear? Hello? Am I audible? Am I audible?
yes, sir.
Okay. So if we have a coil and that coil is carrying some current, and if that current to the coil will obviously produce a magnetic field, and that magnetic field will cause some flux linkage. If the flux linkage of the coil is due to its own current, then that flux linkage is called the self-flux linkage. Say flux linkage of coil say 1 due to its own current, that we define it as psi 1 1. Now say there is some other coil or another some set of coils, there are some currents and some part of the flux line because of those currents there is some magnetic field, and that those fields create some flux linkage in the first coil. So that flux linkage we will call as flux linkage of coil 1 due to some other coils. We will indicate it as M, small m, so mutual. So the total flux linkage of coil 1 psi 1, that is psi 1 1, that is due to its own current, and the psi 1 m, that is due to coil in some other winding. First one is self flux linkage, the second one being mutual flux linkage, right? If for now we consider only one coil, say coil 2, then this one will be psi 1 1 plus psi 1 2 due to current in the second coil. If for the time being we consider only only two coils in question. Now self flux linkage, we understood what we mean by inductance, and so self inductance and mutual inductance. Self inductance is proportional to its own current, and the proportionality constant is self inductance. So psi 1 1 equal to L 1 1 into I 1. So this L 1 1 is the self inductance of the coil 1. Now mutual flux linkage between coil 1 and coil 2, that is proportional to the current I2, where the proportionality constant is the mutual flux linkage, say L1 2, that is the mutual inductance between coil 1 and coil 2. So we have these two things. So if I write this Faraday's law of electromagnetic induction, E equal to d dt of psi, that is equal to psi 1 1 plus psi 1 2, and then if I replace by these quantities, that is L 1 1 into I 1 plus L 1 2 into I 2. Now summation, that is a linear operation, so we can write it as d dt of L 1 1 into I 1 plus d dt of L 1 2 into I 2. We can write it like this. Now can the inductance change? So current can change, we understand current can change uh, with time, but can the inductance change? Yes, inductance can also change if the if something is moving. If something is moving, then the inductance can always change. We'll look at some examples for that also. Suppose we have some static part like this, and we have some moving thing. So there we have some coil here, so dot cross, right? Other places, let us say it is uh, so only let us consider this air gap. Other flux path is changing, is continuous by some other path. So if this is moving, if this actually moves and comes somewhere, say here, where the length of the or the path for flux path, so the area becomes more, then obviously the reluctance is changing with position. So you understand that with if something is moving, then inductance can also change with time. So for that there has to be something, some movement in that. So for that I'll just write for a general case LDT of some inductance into current. So first thing is, let us, because both can actually vary with time, so we will use the concept of partial differentiation. We will hold one at as constant while considering the change in others. So L into di dt plus, then we will hold I as constant. So L is changing. Now L itself does not change, there has to be some change in, say let us consider a rotating thing, then there has to be some change in some theta, something is rotating, that means the theta, the angle is also changing, and this has to be multiplied by d theta dt, and d theta dt is a measure of some omega angular velocity. So L di dt plus I into dou L dou theta, that means the L is changing with rotor position, something that is moving, that we call as rotor. If that is dependent, the inductance is dependent on the rotor position, then there will be some rate of change of inductance with rotor position, and that has to be multiplied by omega, the angular speed. So the d dt of psi Li, that gives us two terms. One is L di dt, another is I into dou L dou theta into omega. So if I write the same thing for these two terms, then I will get L11 di1 dt plus I1 dou L11 dou theta into omega plus, this is for the first term. Now for the second term, L12 into di2 dt plus I2 dou L12 by dou theta into omega. Now let us take the speed dependent, that is the terms which are most speed dependent together, and the terms which are not speed dependent, let us write them together. So one term is L11 di1 dt plus L12 di2 dt. Both these terms actually do not depend on the speed, but the second term, that is I1 into dou L11 dou theta plus I2 dou L12 dou theta. Both these terms are actually multiplied by the speed. So we get this as the general expression for induced EMF for this case, right? So now if we what are these called? So the first case, first term, so both these induced EMFs of certain are called by certain name. So the first name, so this induced EMF is generally termed as transformer EMF, transformer induced EMF, electromotive force. So there is no transformer, there is nothing is changing, only some current is changing in something, and that is creating some di dt, and because of that, because of the inductance, there is some induced EMF in the other coil. So this term is called as the transformer EMF. And the second term, something is rotating, at least for the rotating motor, something is rotating. Because of that, there is some change in the inductance between two coils and or of a single coil. So if something is rotating, and because of that, either there is the change of inductance of the own coil of the same coil in question, or there is some change in inductance, change in mutual inductance between two coils, then there will be some motional EMF, then there is some induced EMF, which is called as motional or rotational EMF. Motional is the more general term. That means something is something is moving, either translation or rotation. If it is rotating machine only, then this can be also called as rotational EMF in case of rotation, in case of rotating machines. So these are the two kinds of induced EMF that we can have, and now we will try to take an example for all these four cases, four examples of induced EMF and try to understand them better. Is there any question till this point? Anything? No. Okay.
No, sir.
Okay. So let us try to consider the first one. Say this one we have already seen. There is some stator, there is some smooth rotor, and there is some winding on the stator, and that is obviously you can see that some dot and cross, some current is flowing through them. Say this current I1 is shown here. So if there is some change in current, so this is time axis, as shown here, and on the bottom, so time. So if the current is changing with time, then the flux, you can see the flux distribution, that also changes. So the flux linkage by the coil, that will also change, right? where whenever current is zero, then you can see there is no flux linkage. When the current rises, you have some positive flux linkage. Then current goes to again zero, there is no flux linkage, zero. Then current goes to negative, flux lines, the direction flips. So positive flux linkage earlier becomes negative flux linkage now, then again it goes to zero. So like this you can see that if you change the current, then the flux linkage also changes, and some rate of change of psi 1 obviously will lead to some induced EMF d psi 1 dt. So if you take the derivative of sine, you will get cos. So you will so if I plot the induced EMF waveform, induced EMF, am I doing it correctly? I don't think so. Yeah. If I plot the induced EMF waveform, then it will look like this. So there will be some induced EMF. There will be some induced EMF across the two windings, across the winding, because the current, because its own current is changing, and because of that there is some rate of change of self-flux linkage, mentioned here as d psi s dt. So there is some d psi s dt, or there is some change of self-flux linkage due to its own current. So obviously if we want to so this is nothing but this coil, if we want to represent, then simply we can represent by one resistance and one inductance, because yes, there is some induced EMF, and that induced EMF is represented by the inductance itself, self inductance of the winding itself, L11, and there is some R1. So this coil whatever coil I have indicated here, this coil, if it has to be represented with a with an equivalent circuit, then this can be because its own current that is producing the change in self flux linkage, and that actually can be captured by putting a simple inductance only. So this coil electrical circuit model is nothing but R and L in series. Now let us go to the second case, which is the case for a transformer. There is a mutual coupling. So we have one coil wound around this one. We have one coil wound around this first one, first limb. Yes, we have some coil wound around the first coil, and we have some coil wound around the second limb also. We have some second coil. Now say we have some current flowing through. Okay, because say we have some, this is coil 1, this is coil 2, we have some current I1 flowing into the first coil. Say this is current that is flowing, sinusoidal current. Because of that, there will be some flux established in the core. So the flux linkage of the same coil will also be, that is the same case as the earlier one. So that will be a sinusoidal quantity. Now if we want to get the flux, actual flux, we have to divide it psi 1 by number of turns of the first coil to get the actual flux. Now this flux will get linked by the second coil. Second coil has some N2 turns, so the flux linkage of the second coil is psi 2 is equal to N2 into phi, and this phi is nothing but psi 1 by N1. So psi 2 is equal to N2 by N1 into psi 1. So psi 2 is here. You can, that is why I have indicated the amplitude difference in psi of the psi 1 and psi 2, considering there is some change in the number of turns. Also it can be due to other reason also. So we have a third limb. So actually all the flux produced by the first coil, that does not go to the second coil. Part of that actually goes to another part, and the third and the third part of the flux linkage will be established in the core. To be told is psi 1 and psi 2 can be can be different also, due to one due to different number of turns, or due to some other alternate flux path, right? Is my screen visible? Yeah, now it has come back. So psi 2, that is also changing with time. So if I try to look at the second coil, then obviously there will be some induced EMF. This is psi is again a sinusoid, so the induced EMF will be cos. It will be like this, right? So this is the induced EMF of the second coil. So we understood the second type of induced EMF, that is also called the transformer EMF or inductor EMF. So earlier case, it was enough for us to represent the whole thing by using one inductance only, but in this case we have to use two coils. So this is the first coil and it has some inductance. We have the second coil that again has some inductance, and there is some mutual coupling between the two. mutual coupling between the two inductances. So because if there is some current through the first coil, and that changes, then there will be some induced EMF across the second coil, which is nothing but the mutual inductance L12 or in this case I should say L21 multiplied by di1 dt is the mutual winding between the second coil and first coil. So that is why the notation goes as 2-1. And on the other hand, if there is some current in the first coil, there is some current in the first coil, then or the second coil, then the resistance will come in here. So there is some current and there is some mutual inductance between the two. So the induced EMF will be L12 into di2 dt. So this is the induced EMF across the first coil. So this is how we represent the induced EMF due to current variation in some other winding. So first one we saw induced EMF due to current variation of the same winding. It can be represented simply by an inductance. And second case, there is some induced EMF due to current variation in some other winding. That is, it is the mutual flux linkage, rate of change of mutual flux linkage that creates the induced EMF, and that is represented by a coupled inductor, or that is nothing but a transformer. So that is how we electrically represent that. Now let us come to the third case, that is induced EMF due to self-inductance variation. So for this case we have the stationary part named as stator. So that is the external or the outer ash color one, and we have some winding, so say dot and cross, and similarly dot and cross. And this is the rotor, the light blue, green color, greenish color, whatever we have, that is the rotor, which is capable to rotate about the center. So actually it can rotate. Now if the coil is excited, now you can see that for this rotor position the flux path length is quite big. So the effective reluctance seen by the coil is actually quite high. Because of that, because of what? Because of that, the inductance of the coil for this rotor position is quite low. But suppose the rotor rotates and come to this position, then there is direct overlap between the poles, as you call it. There is direct overlap between the teeth of the stator and rotor. So the effective reluctance actually drastically reduces, because there is only a small air gap between the stator and the rotor. So the reluctance goes down, so the inductance goes up. So suppose the current remains the same, current is kept as constant, kept at constant at some ampere value, and the rotor is only rotated by some means. Then let us try to see what happens. Initially you can see that at this rotor position there the number of flux lines are quite low. That means the flux linkage of the coil is quite low. But as the rotor rotates, you can see that the number of flux lines increases. It increases at this position. Let me stop and show. It is minimum at this position. It rotates by some amount. It starts increasing. It keeps on increasing. It reaches its maximum value. Now at this instant flux linkage is maximum, but the current is same. Why is the flux linkage changing? Because the inductance is changing. Now it continues to rotate. Again the number of flux lines start reducing, so you have lower flux linkage, and the same thing keeps on continuing as the rotor keeps on rotating. So the self inductance of the coil is dependent on the rotor position, because the inductance of the coil is changing with rotor position. This type of structure is actually called as doubly salient structure. You have poles, the salient poles on the stator as well as on the rotors. So earlier all cases that we have discussed, like DC motor, we had salient poles on the stator, but the rotor was cylindrical. There were only some slots on the rotor, so rotor was mostly cylindrical. But in this type of motors, the rotor can also have some salient poles, and because of which you can have inductance variation of the coil with rotor position, which will give rise to the the induced EMF. So this is the case. We have some constant current flowing through the coil, and as we have seen, the flux linkage of the same coil keeps on changing. It reaches it is minimum it is minimum when the poles are not overlapped with respect to each other, that is this position. But as the rotor rotates and reaches this perfectly aligned position, then actually it reaches the maximum flux linkage, and then again it starts to reduce and comes to this minimum value once more. So what is going to be the induced EMF? Induced EMF for this coil. So the induced EMF, say E1, that is going to be whatever is the d psi 1 dt. So d psi 1 dt. So let us take another one, another. So this is say E1. This is the zero induced EMF. So here in between this point and say this point, there is a very clear slope. It is almost a straight line. So in between these 2 points, the induced EMF is almost constant positive value. In between, at this point you can see that the slope becomes actually 0. So induced EMF will also be 0, and it gradually increases to this positive maximum value. Now again, at this peak, at the peak value of flux linkage, again there is d psi dt, the slope is equal to 0. So at this point, at this instant, the induced EMF has to be 0. So it has to come back to 0 like this. Again, from say some point here to up to some point here, the slope is negative, so the induced EMF will also be negative. In between, actually it comes like this. So this same thing continues wherever you have peak flux linkage, or positive or negative peak of flux linkage. Induced EMF are actually 0. In the positive slope region, induced EMF is positive, almost constant, and in the negative slope region, induced EMF is actually negative and almost constant. So this is the induced EMF. If I try to plot it, this is going to be the induced EMF. Right? You understand what I am trying to do. So we'll have induced EMF like this wherever. So if I try to take only a cycle and try to draw it. So this is the flux linkage psi 1. We have minimum value here, then it goes and reaches some maximum value, it stays at that, and then again it comes down, it reaches its maximum lowest value. Now here at its peak d side dt is 0, here at its negative peak d side dt is again 0. So if I try to plot the E1, and this is E1 equal to 0, this is obviously time. So at this point E1 will be 0, at this point E1 will be 0, at this point E1 will be 0. Between this point and this point the slope is positive, and it increases like this. Here uh, slope reduces and it comes down like this. Then again from this point to about this point it remains almost constant, and it comes down like this drastically. It again falls like this. So this is the induced EMF. This is the induced EMF for the coil. Now you can see, if we want to represent this induced EMF in a circuit, it is not possible to do that with only inductance. Obviously there is going to be some inductance of the coil. So for this type of circuit, the inductance, so what is the inductance of the circuit? Inductance is nothing but L11 is nothing but psi 1 by I1. So whatever is the shape of the flux linkage, because current I1 is always fixed, so if we simply divide the flux linkage by current, we will have the inductance. So the inductance for this winding actually is dependent on time, and more precisely it depends on the position, rotor position. So if we have to represent this winding, obviously we have to put the resistance of the winding, then we will have to put the inductance of the winding. This inductance is not a constant number, L11 is not a constant number, but it depends on rotor position. So we have to mention that L11 as a function of rotor position. Then we will have some induced EMF. We will have to represent it with some induced EMF E, which again is a function of both. Actually it is function of both. It is function of the current I1 as well as the rotor position, and current is what is flowing through the coil. So if we have to represent this type of coil, then we have to represent it with equivalent circuit diagram like this, where we have some resistance representing the resistance drop across that winding. We have some inductance. That inductance is not constant, but it changes with rotor position. That is what I have mentioned, L11 as a function of rotor position theta. And we have some back EMF, induced EMF, that we have to use a voltage source type of symbol, and the magnitude of the voltage induced, that actually depends on the rotor position, as we can clearly see, but it also depends on the current that is flowing through the coil. If I do the same thing for different currents, we'll be able to see that the induced EMF will be different. So this is how to represent this type of coil, where the self inductance is varying, and this is the case for a machine called SRM, or the switched reluctance machine. Probably I'll quickly go through the fourth case also, and we'll have a brief recapitulation of the whole thing. So there can be another case. So we can have two coils. So I'm continuing with the first case, where the DC machine case, basically we have some field and we have some current flowing to the field winding. So the first winding, coil 1, and we are considering only one coil in the on the rotor, say the blue one, whose directions may be say if this is the direction, then flux line direction will be upward, so this one will also go upward. So this one will have to be cross and this one will have to be dot if it has to be negative, because simply because here it comes as negative, that is why so that means I must have taken this direction for the second winding current direction. So for mind you, second winding is not carrying any current, so first winding is carrying current and that is constant, that is always constant. Now what happens if this is rotating, this rotor, it's rotating just like here, just like for this position you can see that the current, due to this current there is some flux lines and the flux lines are linking the blue coil. Now if I rotate it, then you can see that the flux linkage of the second coil, that keeps on getting changed. Now if I try to stop at multiple points and show you, at this point all the flux lines are linking, this coil, all the flux lines, you can see this is the flux line that is going and linking, this is the another external flux line that is going and linking the first coil. Now if I go little ahead, say here, here only the flux lines that flow from this point to say this point, they are actually, or yeah, so all the flux lines that are flowing like this and flowing like this, they are linking the coil, but the flux lines that are again I'm back here, so yeah, so the flux lines, erase. Now if you consider, earlier you saw all the flux lines generated by the stator are actually linking the second coil, but in this case you can clearly see some flux lines. Say I'll show one representative flux line. Say this is one flux line. Say this is one flux line that does not link the coil, that does not enclose any of the conductors of the coil. Or similarly you can also have this flux line. You can also have this flux line which similarly does not enclose any conductors of the coil. So that means if because of the rotation of the rotor, the flux linkage, although the current of the first winding remains the same, the flux linkage of the first coil also remains reasonably the same. This is flux linkage of the first coil, but the flux linkage of the second coil changes due to the rotation of the coil, rotation of the rotor. Now if I go further forward, if I reach the perfectly vertical point, then you can see that all the left side flux lines, all the left hand side flux lines, all the left hand side flux lines, they are going and flowing like this, they are not linking the coil. And on the right, all the right hand side flux lines, they are going and flowing like this, and they too are not linking the coil. So in this case we have absolutely zero flux linkage as indicated by this point. So to start with, if we now look at the flux linkage of the second coil, we have negative peak flux linkage for the initial point, then it gradually remains almost the same, then it gradually increases or reduces in magnitude to 0, then it increases in magnitude to positive value, it reaches almost the peak, it remains almost constant, then again it comes down to 0, then it goes on reducing to negative value, grows in magnitude, reaches negative peak, then almost remains the same, almost remain constant. Now if I try to plot the induced EMF, that is d psi 2 dt, what that will be? Say this is the zero line for the flux for the induced EMF. Between this point and this instant it is reasonably 0. Again between this instant and this instant it is reasonably 0. Again between this instant and this instant it is reasonably 0. I'll name this instant 1, 2, 3, 4, 5, 6. So between 1, 2 it is 0, between 3, 4 it is 0, between 5, 6 it is 0. In between 2, 3 it rises with almost a constant slope, so the derivative will be constant, the induced EMF will be constant. So it will be some shape like this. And again between 4 and 5 it is following with nearly constant slope, so we have some negative induced EMF. So this is the type of induced EMF that will be there across one coil that is rotating in this type of a scenario, where the first coil is having a constant current and due to that almost constant flux linkage of its own. But the second coil, the flux linkage changes, and because of that there is some induced EMF. Now in this case what is happening? In this case actually the mutual inductance between the first coil and the second coil, that is changing. Mutual inductance is changing. Because of that, because the current, there is no current in the second coil. The current in the first coil, that is not changing, unlike the case for a transformer. The current is constant. But because of the rotation, the alignment of the coil axis, so the first case the coil axis is here, that is in line with the first coil axis, so the mutual linkage is maximum, so flux linkage is also maximum in its magnitude. Then as it rotates and the coils basically come here and here, then this becomes the new flux axis, or the axis of the second coil, which is perpendicular to the first coil axis. So the mutual linkage becomes 0. So you have 0 flux linkage here. Similarly, as it rotates, because of the rotation of the second coil axis, the mutual inductance between the two changes, and that comes out as the induced EMF due to the mutual flux linkage. Now in this case, how to represent the coil? How to equivalently represent the coil? How to represent the coil with the equivalent circuit? So in this case, obviously the coil has to be must have some resistance. Now there has to be some inductance also, but the inductance, what is in that inductance of the coil, first coil? That is nothing but, so we have to represent two things: first the first coil equivalent circuit, and then second coil equivalent circuit. First coil, the flux linkage remains almost constant, so we can reasonably represent it with a constant inductance, say L1, and some resistance R1. So this becomes the equivalent circuit for the first coil. Now for the second coil, which is now not carrying any current, but that also should have some resistance, that must have some inductance also, and that must have some induced EMF also. So this becomes the equivalent circuit of the second coil. Say some induced EMF, that obviously will be dependent on the rotor position, the first coil First coil current may also be first coil current may also be responsible for that, and this resistance R2 will be reasonably constant. And L2, what about L2? L2 will also be a function of the rotor position, because when if you consider, if the second winding is excited, then at this rotor position the inductance is maximum, because the air gap is quite low. But at this point where the coils are here, then the coil axis, along the coil axis the air gap is large, so the inductance will also change. So this case also, the self inductance will also depend on the rotor position, and there will be some induced EMF due to the rotor position and the first winding current. So here we conclude the 4 types of induced EMF. The first 2 types being the transformer EMF, which is due to its own current or current in some other winding, and the second case, it is due to inductance variation due to rotation. First one, self inductance variation, and second one, mutual inductance variation. So this sums up all the 4 cases of induced EMF. So if you don't have any question, let us conclude now. Do you have any question, Yug?
No, sir. Fine.
Okay.
Right.
Things are clear, right?
Yes, sir.
Okay. So thank you. Let us stop it. Good night.